Welcome back. Today we're going to talk about the one sample z-test, which is not to be confused with z-scores. Remember, z-scores are standard scores that help us identify how far or how close an x value is from the mean. By knowing the z-score number of an x value, we also know its probability. So, the one sample z-test is a very important test and we use it to study zombies. Okay, that is a bad joke. The one sample z-test is used to examine differences between a sample and its population. Essentially, what we're trying to do by running a one sample z-score, z-test rather, is to see how similar or how different our sample mean is from the population parameter. In a perfect world, our sample should be very close to our population of interest. We always aim to select the most representative sample, but of course, error is always going to be part of it. Your book has this really handy table which helps you identify what tests you need to use depending on the type of data you have. From now on, we're going to cover various inferential tests, so knowing when to run which test is crucial. SPSS will pretty much run everything you tell it to, but you can imagine that your results will be useless if you did not meet the assumptions and criteria for the selected test. As you can see on this table, the very first question you need to ask is if you're examining differences between variables or between a sample and a population. In our case today, we will choose the latter, thus a one sample z-test is the appropriate test to use. One of the very basic assumptions in order to run a one sample z-test is that the population is normally distributed. Going back to the previous chapter, you recall that most sample means should be very close to the population mean. Critical regions define which values result in rejecting the null hypothesis. So in the case of a one sample z-test, the null hypothesis will be that the sample mean is equal to the population mean. Thus, if the sample mean differs greatly, in fact differs as much as to land on the critical region, which would be right here, the two tails, right? Then we will have to reject the null hypothesis. And here's your favorite, another formula. This is the formula for the one sample z-score. Just by looking at it though, you can see all we just talked about. On the numerator, you have the sample mean, and from it you subtract the population mean, okay, the mu, to see how different the two are. On the denominator, you have what is called the standard error of the mean, or SAM. The standard error of the mean is the value we would expect to get by chance alone, given the variability of all possible sample means from a population. The cool thing about it is by using the standard error, we can use our old friend the z-score table to determine the probability of something happening or not. Apparently, the size of the standard error will affect our z-test statistic. Right here, you can see how we actually compute the SAM. So it would be the population standard deviation divided by the square root of your sample size. Let's look at an actual example so we can go through the various steps of solving a one sample z-test statistic problem. So here we have a population of flamingos. Their average height is to be 60 inches with a standard deviation of 10. Researchers want to know if coffee consumption will have an effect on their height. In other words, if we start giving flamingos coffee instead of water, would that affect their height in a positive or negative way? I know what you're thinking. Brilliant example. Regardless of what you think, our scientists went ahead and selected 30 flamingos who have drunk coffee while growing up, and they measured their height. They found that the mean height of our sample is 49 inches. So the question is, how similar is our sample to our larger flamingo population? If coffee had no effect, then their height should be very similar. If coffee had an effect on their growth, though, we should see either a positive or negative difference between our sample and our population. In order to solve this problem, we need to go through what we call the 7 steps to hypothesis testing. And here they are. We first state our null hypothesis and alternative research hypothesis. We set our alpha level. Remember, that means how confident we want to be and how much do we want to leave to chance. Our most common alpha level is going to be 5%. We are willing to risk that much, which means that we want to be at least 95% sure that the results are not due to chance. The third step is identifying the correct test statistic. In this case, we have a sample and a population. So by using your table, you can see that the appropriate test would be a one-sample z-test statistic. We go ahead and compute the test statistic and we come up with a value. We then identify our critical values necessary to reject the null hypothesis on our alpha level, based on our alpha level, and of course if your hypothesis is directional or not. Note here that the non-directional test requires you to split your alpha level because you simply look for differences, so the differences might lie in either side of the curve. The sixth step is to compare our test statistic to the critical values we just identified and make a decision. Do we reject or fail to reject the null hypothesis? Last, we state our results. So back to our example, the null hypothesis should state that there is no differences in height between our coffee drinking flamingos and the general population of flamingos. Our alternative hypothesis will state that there is a difference between our sample and the population because we suspect that drinking coffee does something to their height. Let's go ahead and set our alpha level to 0.05 or 5%, which is the most common alpha level, and why that might be. Think what would happen if we set our alpha level to 0.01. Would that make our research hypothesis easier or harder to prove? You may want to pause at this point and think about it for a minute. It would actually make it extremely difficult to prove and most likely would run into a type 2 error since we accepted a false null hypothesis. Remember, by setting our alpha level to only 0.01, that means we want to be 99% sure, which is very, very difficult to prove. In other words, we're being extremely conservative and we might run into errors because of it. We choose to run a one-sample z-test based on the fact that we're examining differences between a sample and a population. And to make our lives a bit easier, I would recommend you that you always calculate SEM first, and then we can plug your results into the regular one-sample z-test formula. So to find the value of our denominator, we have to divide our population standard deviation with the square root of our sample size. 10 being the standard deviation divided by 5.48, which is the square root of 30, we end up getting 1.82. To finish our computations, we find our sample mean, which is 49, and we subtract the population mean, which is 60, and divide with a SEM. Okay, down here. Our z-test statistic is negative 0.6.04. Well, let's see. Is our result significant or not? Well, we do not know yet. Now we have to think, what are my critical values? How do we find them? Well, first things first. Is our test directional or non-directional? Read the problem again. You're looking for differences either being positive or negative. So that means we do not care what type of effect coffee has on flamingos. We just care if it has an effect. Okay? So in simple words, our test is going to be non-directional. Since it is non-directional, we have to take into considerations both sides of the curve, so we have to split the alpha level. So each side will get 2.5%, right? 2.5% and 2.5% is 5% total. Now what I want you to do is go to your z-table and find a z-score that corresponds to a 47.5% area, which is from here to here. Okay? Remember that the table gives you the value from the mean, okay, the value from the mean to the chosen value. If half your curve is 0.50 or 50%, then taking away 2.5% leaves you with 47.5. That's how we get that number. The critical value that corresponds to that number is going to be 1.96. Now, since it's a two-tailed test, okay, we're going to have negative and positive 1.96. Your test statistic needs to be greater than your critical values in order to reject the null hypothesis. In order to claim that there's significant differences between your sample and your population. Therefore, what we need to do is, do we have a test statistic that is higher or lower than plus or minus 1.96? Well, our z-test statistic is negative 6.04, which is way lower than negative 1.96. Guess what? We get to reject the null hypothesis very safely. Our results are indeed significant. Final step is to state your conclusion, which is what? Since we reject the null hypothesis that the alternative must be true, okay, which stated that there are differences between our sample and the general population of flamingos. By looking at our test statistic, we see that it is a negative value. So we conclude that flamingos who drank coffee are indeed shorter than the flamingos that did not drink coffee growing up. Why is that? Well, that is something that we will answer at a later time. Great job, everyone. You survived one more lecture, and now you're ready to rock every single one sample z-test statistic problem that's going to come your way. Take care.